Alrighty, folks, it's your friendly heavy physics teacher again, and this time I'm doing a combined lesson because it just so happens that the college physics and Regents physics class are at the same point with their online stuff. And interestingly enough, for the college physics class, Unit 10, Lesson 4 is essentially the same lesson that the Regents physics class has for lesson 1 of unit 11. Okay. All of it is an introduction to the characteristics of waves, what waves are, and how we go about measuring them. Okay. It's going to draw on many of the things that we did with simple harmonic motion for the college physics guys that we did in the first 3 lessons for Unit 10. For the Regents physics guys, we did this back when we looked at pendulums, back when we did conservation of energy. All right. So if you can still have somewhere your notes on pendulums from way back when we did the conservation of energy unit, and looked at period of a pendulum, then that will help you as we talk about some of the terminology with wave characteristics. Okay, so what are waves and why do they become important for us? All right, waves are a divergence from classic physics as we've known it. Okay, up to this point, we have talked about the world, the universe, in terms of physically identifiable, physically interactive things. All right, all of Newton's laws were about how forces interact, how forces change motion, da 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 da. All of that. Okay, electricity is simply a manifestation of these forces and of energy, and yet we're looking at energy that way. We're looking at electricity. We're looking at magnetism, and all of a sudden, things are happening that can't be directly explained using Newton's laws. And that's where the whole concept of wave theory and how it was so different from Newtonian mechanics that it actually, for a while, was thought of as a whole different area of science. Okay? And yet it's not. The two interact. Okay? Um, we talked about transfer of energy before. I'm going to go back and use my billiard table analogy. Okay, imagine a billiard table. Okay, you've got pool balls on one end, you got the cue ball on the other, and if you hit the cue ball, all right, you've given energy, the energy of the motion of your arm, the energy of the nutrition energy that's in your muscles gets transferred into the cue stick, which then gets transferred into the cue ball by the collisions, by the physical forces that are interacting there. And then the cue ball gains kinetic energy. And that kinetic energy, some of it is lost as it rolls across the table, but not a lot. And then it whacks into that rack of billiard balls. All right. And the energy gets transformed into them. The energy that came in with the cue ball motion decreases, bounces off, moves somewhere. But if you were to add up all of the kinetic energies of all of the motions of all of those billiard balls after that collision, taking into account that you heard sound, taking into account that there's rolling motion, if you add up all of that energy, the energy of the motion of the cue ball coming in would be equal to all of the energy present in all of its forms, even the lost energy because of sound, because of heating, because of the reverberations, the internal energy. But if you accounted for that, then the energy of your arm hitting the cue ball, the energy of the cue ball rolling across the table, the energy, then that the energy of all of the balls separating in whatever manner they do, that's all the same. That is energy transfer by motion of mass and collision of mass. That's classic energy transfer. Right now, you are receiving wave energy transfer. The energy of my voice is vibrating the air molecules here in my throat. These air molecules are not traveling across the room over here to the microphone on my laptop. The air I'm breathing out here probably is getting about this far away from me before it becomes diffused into the rest of the air of the room. There is no, maybe one molecule of the air that I'm using to speak is actually getting over to the microphone that's on my laptop. Okay? And yet, you're hearing the sound. Energy transfer. It's creating this vibration, this compression and separation and compression and separation and compression and separation of the molecules. That vibration enters the microphone. It creates a vibration system with the microphone. That could be a coil of wire that's wrapped around a magnet, and as the coil of wire is vibrating due to the pressure waves of the air that's attached to the cone, that creates an EMF in the coil. That EMF is then transferred to the internal electronics of my laptop, which is then transformed into an electromagnetic wave that goes to my router, that then goes out through the wires to another radio transmitter. That signal is amplified. It goes through space, all the way probably out to some satellite out there orbiting the Earth, bounces back to some other location nearby, or it's traveling through the wires to your house, and then out of your computer, out of your phone, and it vibrates the air in your room, and then that air gets vibrated at your ear. At no time did any of the air coming from me get to you through this system. Energy moving through space, and it's moving through space by the means of waves. Okay? And as you can see, we can get really complex with how we look at all of these levels of interaction. Okay? And yeah, it's my job to think about that because I'm a physics teacher. All right? But it's also your job to be able to understand that. And so that when weird things happen that aren't normal, don't obey what we would normally expect to happen. We don't have to put it off as, oh, that's magic, or that's no. It can be explained. We just have to figure out the phenomenon for explaining it. Okay? All right, so let's look at our definitions. Let's define how waves move. Okay? All right, first off, a wave. A wave is a patterned disturbance of the material or space that energy moves through. Okay? And yes, we can have pattern disturbances of something moving through a space that has nothing in it. We'll get to that in a little bit, but spoiler, we're talking about electromagnetic waves moving through a vacuum, right? But waves are the disturbance of the energy moving through the material. The material itself isn't moving. Waves are energy transfer. That is energy moving from one point to another, possibly going through a physical medium or going through non-physical medium like a vacuum, all right? but it's the wave, the energy transfer going through. All right. So the matter itself may move, but it only vibrates. It doesn't move with the wave. Okay. So that's a clear difference between what Newtonian mechanics says about transfer of energy. Two things have to bump into each other in order to get one to give the energy to the other. Okay. Um, Waves let energy move through, and you don't have to have the physical matter carrying the wave and then stopping its motion, and the next thing picking it up and carrying it on from it. Okay? Waves are vibrations. And because of that, we can use the vibrational characteristics that we've been talking about to describe them. Okay? So, since waves are vibrations, we can use the characteristics of period. Period is time to make one vibration, time to make one oscillation. Frequency. Frequency is the number of vibrations per second, or the rate of vibration. Amplitude, how big the wave is, how far the wave displaces something from its equilibrium. A new term, wavelength. Wavelength is a distance. Wavelength is the distance that the wave makes in one full vibration. It's the distance the wave travels in one full vibration, which means that it is the distance between 2 points on that wave that have the same amplitude and the same motion. Okay? So, new term, wavelength. Wavelength is the distance a full oscillation travels as the wave moves through a medium. And then, of course, speed. Now, we've talked about speed prior to this. It is a classic measurement of how fast something moves. Well, if we've got energy traveling and it creates a distance for the disturbance to take place, it's distance divided by the time it takes that disturbance to make a full cycle, then distance divided by time is speed. Okay? So, let's talk about how we can make these measurements using what we can quote unquote see with a wave. Okay, the most common waveforms, the most common way that waves vibrate the medium are either transversely or longitudinally. A transverse wave is a wave that vibrates the medium across the path of travel. The motion of the vibration is perpendicular to the motion of the travel of the wave. So we have here an example where I'm saying, okay, let's say this is a string, all right? And if you shake the string up and down, that's going to get that motion energy of your hand waving up and down. It's going to move it down the string. The string's elastic properties will cause it to move down the string. Okay? So when you vibrate your hand up and down, that is transverse to the motion of the energy traveling down the spring. Okay? So here we say that over here is the source of whatever this wave is, and the wave is traveling this way across this page. So a wavelength is the distance of one cycle of a wave as it moves through the medium. So here, we start at one crest of the transverse wave, and it goes down and comes back up, and we have the second crest. All right. Now this one happened earlier. This one happened over here and moved through that distance to get to there. Then this one is going to move again, and it will end up over here where this one is now. All right. I realize it's a stationary representation. It's kind of hard to see it moving as it travels along. All right. But think of these as ocean waves. Think of these as a ripple in a pond. And the ripple is that hump is what's moving along. All right. But the water itself is staying there. The water itself is just doing that as the ripple moves through it. Okay. Longitudinal waves. We don't see longitudinal waves. All right. They are very hard to witness. We can feel them though. Longitudinal waves are generally pressure waves. Okay. And so what this is normally whatever the medium is that would be this, think of it as individual particles that are equal distance apart. And then I do this, I knock on this end or I push this end. Well, that push scrunches these together. All right. And so that push causes the next one to scrunch and the next one to scrunch. And then as that scrunch moves down, these over here start separating. And that separation will also travel. And as long as you keep that push in, pull out going, this is going to scrunch and stretch and scrunch and stretch and scrunch. And that scrunching and stretching is the longitudinal wave moving through the medium. This is a sound wave. This is what sound waves do to the medium. Okay? So the pressure waves going from me to the microphone here are creating this scrunching and separation, scrunching and separation, and scrunching and separation of the oxygen and nitrogen and stuff that's in the air that we breathe and that you are able to hear with. Okay? But as there was a wavelength with a transverse wave, there's also a wavelength with a longitudinal wave. And notice I've drawn it from the middle of the scrunched in area here. This is known as a compression. To the middle of the scrunched in area over there, the next compression. This one happened first. This one's moving along after it. All the way over there, that was the first one that was made. That was made back here at the beginning, and it moved down. This is the first one. This is the second one. This is the third one. Notice that I've also shown a wavelength from where the spread out portion is. This, for a longitudinal wave, the spread out portion is called a rarefaction. Look that up on the notes page. Rarefaction. Okay? So from this rarefaction to that rarefaction, it is a wavelength apart. Okay? Wavelength. The distance that a wave travels to make a full cycle. The distance that a wave travels to make a full cycle. All right. Now, I'm using this term medium. The material, the space through which a wave moves. Okay, so let's define that. Medium. All right. Medium is the material and space, sometimes or, but the material and space a wave is moving through. Can be physical, all right? Physical is anything that has matter. The air you're breathing is a physical medium. It has matter in it. There's nitrogen atoms, there's oxygen atoms, there's dust particles, there's all sorts of stuff in that stuff that you're breathing. So it's a physical medium. Water is a physical medium. And obviously solids, metals, the board here, what have you, those are all physical mediums. Okay? Waves can pass through them. All right? If you've ever gone to a steel fence and had a friend stand at one end, You can tap on the steel fence a long way away and you can hear those taps. Okay. My dad used to have a camp up on the Great Sacandaga Lake, and when I would vacation up there in the summer, I could tell when a boat was coming because I'd dive under the water, be swimming under the water, and you'd hear the motor through the water, and you'd come up above the surface and you wouldn't see anything. Well, anybody who's been up at the Sacandaga Lake knows it's a big lake, and you can have the boats pretty far away, but because the medium, the water is a better medium for sound to travel through than air, it actually travels more easily through the water, and so you can hear it more easily underwater than you can through the air. Okay, kind of a weird thing. All right, now a vacuum. Technically, a vacuum is any space where there are less than 100 particles in a cubic meter. That's pretty much the scientific definition of a vacuum. All right. If you've got 1,000 particles in a cubic meter, oh, that's still considered a vacuum. You know, outer space is considered a vacuum because in any given cubic meter, you are not going to find a lot of particles. All right. Now, some of the places of outer space have a huge density of particles, and thank goodness we are located on one of those places in outer space where there is a massive density of particles, known as the Earth. Thank goodness. All right? But the only type of wave that can go through something that has no particles in it, and we've proven this experimentally, and every morning you wake up and look out at the sun, it's proven to you experimentally that only electromagnetic waves and gravity waves are known to be able to go through a vacuum. Electromagnetic waves do not require a physical medium for them to move from one place to another. Gravity waves do not require a physical medium for them to move from one place to another and create an interaction. Okay? Now, can they move through a physical medium? Sure. All right. Electromagnetic waves go through glass. All right. Electromagnetic waves travel through wires. So they can go through physical mediums, but they're the only ones that don't require a physical medium for them to be transmitted from one place to another. Okay? If the wave can only be transmitted via a physical medium, we call it a mechanical wave. Sound is a mechanical wave. If it can be transmitted through a vacuum, it doesn't require a physical medium. Then they are pure energy waves. Gravity waves are pure energy waves. Electromagnetic waves, light, heat, X-rays, ultraviolet, infrared, microwaves, those are pure energy waves. Okay? Now, the speed of a wave is dependent on the medium through which it's moving and the wave characteristics. Okay? So, the speed of a wave is always constant in any given medium. So, if you have air at a specific temperature, the speed of sound through air is going to be one value, no matter what kind of sound it is. Could be a low sound like this, could be a high sound like this. But the speed of that sound does not depend on the wave characteristics in that medium. Change the temperature of the air, and you're going to change the temperature of the wave. Okay? If you're using some other physical medium, say a solid, say steel, okay? And if you put that steel under a lot of tension, you can actually speed up how quickly the wave moves through that. If it's not under a lot of tension, it slows down. So, how do we measure the speed of the wave? Speed of the wave equals the distance of one wave divided by the time it takes to make one wave. The distance one wave travels in one time period. So distance divided by time, speed. Well, since frequency is the inverse of period and frequency is vibrations per second, if we take the frequency and multiply it by the distance of one vibration, that also gives us the speed. Okay? Because if you think about that, one vibration times the rate of one vibration, how quickly it takes to make one vibration, there's our speed. All right? This equation is the one we're going to use most often for when we talk about waves, because frequency is going to be the characteristic of a wave we most often will use to identify the wave. We'll rarely talk about a wave's period. We sometimes will, especially when it is a very low frequency wave. But most often we talk about the wave in terms of its frequency, how quickly it's vibrating. Okay? If you change the medium, you change the speed. If you don't change the medium, but change the wave, the speed of that wave stays the same, but maybe it's a higher frequency, so it's going to be a shorter wavelength. That's the change that you're going to get. Okay? Okay, let's review what we've talked about. Waves are moving away from the way we classically think about energy transfer. Prior to this, it had been physical matter moving along, crashing in, bumping into something else, and in that bump, an energy transfer occurred. Now we've got a situation where there's an interaction between these two. There's some sort of force connecting them, gravity, electromagnetic, and this interaction over here creates a interaction over here. Well, this passage, the passage of that interaction through space is the wave. Okay? Wave characteristics. Since it is a vibrational aspect to this motion of the energy, we use the characteristics of period, time to make one vibration, frequency, rate of vibration, in other words, number of vibrations per second, amplitude, how big the wave is, all right, how much it caused the medium to vibrate from equilibrium, speed, and wavelength. 5 characteristics of waves. Okay? Wavelength is the distance it takes the wave to travel in one full vibration. Speed depends on the medium. You change the medium, you change the wave's speed. Change the wave, though, and not the medium, and you've changed either frequency or period or amplitude or wavelength, but you have not changed speed. Okay? Please be looking for the Wave Characteristics Lab. It's a Physics Education Technology Lab associated with this. I'll be sending you an email out with that and when that lab will be due in the future. Thank you all for watching. Thank you all for listening. This has been your friendly heavy physics teacher with a lesson on waves. Great to see you all, and hopefully very soon I'll be seeing you back at school. Bye-bye.